transitioning to the next speaker, I'm really happy to welcome you here on stage. It's Kiwan Maeng. Want to mention he just took a position as a first-year assistant professor at Penn State, but now today is presenting work that is done at Meta. And the title of today's work is Toward Fair Federated Recommendation Learning, Characterizing the Interdependence of System and Data Heterogeneity. The floor is yours.
Hey, thanks for the wonderful introduction. I am Kiwan Maeng. So this is, like you said, the work that I have done while I was at Meta. So start right away. So the clock is not moving. Is this? There's the countdown clock. Maybe I can go on. Anyways, brief 1 minute introduction on what I'm going to talk about today. So recent studies increasingly, recent studies increasingly started to look into training a recommendation model using federated learning to enhance user privacy. When training a model using federated learning, Haiyu work extensively studied the effect of data heterogeneity and system heterogeneity. However, they failed to look into any potential correlation between the two, simply assuming that the two heterogeneity are independent of each other. In this work, we aim to study if such an assumption is true, and if not, what can be a potential effect, especially in terms of fairness. So this is going to be the overview of the rest of my talk. First, I'm going to talk a little bit about the motivation and the background, and then I will talk about the two data and system heterogeneity and a potential correlation between the two. Then I will talk about our simulator, which can simulate realistic system-induced data heterogeneity, which is the correlation between the two heterogeneity. Then I will show you some evaluation results and conclude my talk. So a little bit more about the background. To train a recommendation model without having to collect raw user data, people have started looking into federated learning. To train a model in federated learning, instead of collecting raw user data, on each round, the server selects a subset of the client to participate and sends the model that needs to be trained to each client. Each client then train their model on their local device using their local data, and when the training is done, they send back the model to the server where it gets aggregated and one global server-side model is calculated. And this process repeats until the model converges. When doing federated learning, there are two types of heterogeneity that can complicate the training process. The first is called data heterogeneity, which refers to the fact that different clients may have different data distribution. For example, some clients may like apples more, while some other clients may like bananas more. And depending on their fruit preferences, of course, the recommendation system will have to recommend different items to the user. There's also something called system heterogeneity, which refers to the fact that some clients may have low-end devices with limited computation and communication capabilities, while some other clients have higher-end devices which has more computation or communication capability. This imbalance in system capability causes low-end devices to become the bottleneck of the entire training process. So some prior works proposed tier-aware optimizations that essentially applies a more aggressive optimizations to lower-end devices to balance the overall computation or communication time between different tier devices. Some of the popular tier-aware optimizations, for example, are shown here. Google's smart keyboard's next word prediction model simply disallows low-end devices from participating in the training process entirely. This is a very radical form of tier-aware optimization. Some other works, instead of entirely excluding low-end devices, often proposed running a degraded computation or communication on low-end devices. For example, they pruned or quantized the gradient more severely on lower-end devices to reduce the communication cost, or they used less channels or smaller models on low-end devices to reduce the computation time. So that was the brief background. And these optimizations that I just talked about were all shown to be very effective in prior works. However, they had one big assumptions in common about data and system heterogeneity when they were testing out these optimizations. That is, when simulating data and system heterogeneity, what prior work essentially did was they first started from a data set with data heterogeneity, and then they randomly assigned to each client a synthesized or collected system heterogeneity statistics. For example, they just randomly assigned like this client has high-end devices. Let's assume this client has low-end devices and evaluate the result. By doing so, they are essentially assuming that data heterogeneity and system heterogeneity has no correlation. In other words, the probability of liking an apple or bananas are essentially the same regardless of the device tier the user has. In such a synthetic scenario, even if you apply a tier-aware optimization to low-end devices, it does not really introduce any fairness problems because high-end devices and low-end devices essentially have the same data distributions anyways. However, you can think of a hypothetical case where low-end devices tend to like apples more for some reason, while higher-end device users like bananas more for some reason. In such a hypothetical scenario, you can see that data heterogeneity and system heterogeneity are tightly correlated with each other, and we say that the dataset has high system-induced data heterogeneity to refer to such phenomenon. So what does the real-world data look like? Due to the interest of time, I will not show you real-world data statistics. It is in our paper. But by analyzing real-world data from production recommendation models, what we found was that real-world data indeed has a high system-induced data heterogeneity. Data heterogeneity and system heterogeneity are tightly correlated, just like the example we saw, instead of what prior work assumed. And you can easily imagine that when there is such a high system-induced data heterogeneity, if we apply a tier-aware optimizations, for example, if you simply disallow low-end devices from participating, what will happen is that the end model would not work very well on low-end devices, which is mostly Apple lovers, because the model is highly biased towards high-end devices, which is mainly banana lovers. Again, is this effect real? With production data, we saw that this fairness effects can happen in real-world data. We applied popular tier-aware optimizations to our real-world data and saw up to 16.7 times more accuracy degradation on lower-end devices compared to higher-end devices. Again, this kind of fairness problem was not observed or reported in any of the prior work to the best of our knowledge because prior work during their evaluation assumed the data heterogeneity and system heterogeneity did not have any correlation. So how can you study these kinds of effects when you don't have access to real-world data like us? That is why we designed RF², which is a simulator that can simulate realistic system-induced data heterogeneity using open-source datasets. RF² first takes a popular open-source recommendation dataset, such as Taobao Ads Click Display dataset or Movie Lens dataset, and it synthesizes different levels of system-induced data heterogeneity on top of the open-source datasets. It particularly uses Dirichlet distribution to control each device tier's affinity to different items. What I mean by that is that it can make some device tiers like apples more, while some other device tiers like bananas more, just like in our earlier example. And there is a parameter alpha, and by tuning the parameter, we can make the system-induced data heterogeneity really high, as we saw in our production example, or we can also make it very low, and that will be similar to what prior work assumed. With the synthesized system-induced data heterogeneity, RF² supports training popular recommendation models using federated learning, such as DLRM or DIN, and using popular tier-aware optimizations. And finally, it can estimate the resulting accuracy and fairness. For more details about our system, please again refer to our paper. And now let's look at some interesting results. So we evaluated RF² with 2 different open source data sets, 2 different models, 6 different levels of system-induced data heterogeneity, and 6 different tier-aware optimizations. The tier-aware optimizations that we studied can be are shown here. We studied excluding low-end devices, which was the approach Google Smart Keyboard was using. We also overselected the clients by 20% and dropped the 20% slowest clients. We also tried using different gradient pruning based on the device tiers, different gradient quantization based on the device tiers. We looked at 2 different gradient quantization methods. And finally, we also looked at using different channel size depending on the client's device. For the fairness metric, we used maximum difference in accuracy change. So I will gonna only show you a subset of the result because of the interest of time. So here I'm showing the result when we exclude low-end devices from training. And there are 6 bars. Each bar shows the different level of system-induced data heterogeneity. From the left, no system-induced data heterogeneity as what was assumed in the prior work. All the way to the right is very high system-induced data heterogeneity. And the y-axis is the fairness metric, which is higher means more unfair. What you can immediately see from the bars is that even if it's the same optimizations, depending on the level of the system-induced data heterogeneity the data set has, the fairness implication can be very different. We saw up to 15.8 times fairness difference in this particular example, and for some other cases, we've seen up to 41 times fairness difference. So this implies that if you assume no system-induced data heterogeneity in your evaluation, just like what prior work did, you can mispredict the real fairness impact. You can downplay the fairness impact by up to 16 to 41 times. We now also show the result from other optimizations as well. So here, what you can see by comparing different groups of bars is that these are all similar optimizations with similar overhead, but you can see from the height of the bars that the fairness implication can vary significantly between different optimizations. Again, this effect can be only seen if you assume a realistic system-induced data heterogeneity in your simulation. Otherwise, these interesting effects is not really visible. So here you can see that gradient pruning is more unfair, and even between gradient quantizations, depending on exactly what quantization method you are using, some are more fair than the others. Finally, we also saw that best accuracy optimization is not necessarily the best in fairness. So if you compare these two groups of bars, the first bar at the end showed better average accuracy, but the second group of bar was much more fair, as you can see from the height of the bars. This implies that it is very essential to study fairness as well as accuracy when you're studying federated learning and different optimizations, especially in, again, realistic system-induced data heterogeneity data set. You can see more characterizations and results in our paper. And this is my final slide. I will just conclude my talk. So we have seen that system-induced data heterogeneity exists in the real world. It is very real, and it can cause real fairness impacts. So RF square is a simulator for you to study those kind of effects when you don't have access to real-world data. And our evaluation shows that RF square can simulate such a realistic effect, and you can have interesting observations about your optimizations that you are designing. This is the end of my talk. Thank you, and I will be happy to answer any questions.
Thank you. A lot of questions are flowing in. Let's start with this one. Are we implying correlation or causation between data system-induced heterogeneity? Data and system-induced heterogeneity?
So I guess the question is whether it is more like a correlation or causation. So that is what we don't know for sure because we haven't analyzed the real-world data to that extent. But what we tried to do was whether it is actually a causation or correlation. We wanted to simulate similar effect on open source data set with what we were observing from production data.
Okay. Does improving system accuracy for low-end devices decrease system accuracy for high-end devices, or is there a way to balance potential accuracy trade-offs?
So that's a really good question. So this paper is more about characterization and introducing the simulator. So it can happen where improving low-end devices accuracy can, sometimes it can degrade high-end devices accuracy. And whether that's a good thing or not, it depends on your system's goal. But we believe that this framework can promote future researchers to study those kind of effects and possible solutions.
Okay. Then there's an interesting one. I find it interesting. What is the fairness definition here? Less powerful devices do less computation and contribute less due to resource constraints seems fair by intuition?
Mm-hmm. Yeah, so it's, again, a really great question. So the metric we used was simply whether the accuracy degradation after applying the optimization is similar between devices or not. And because low-end devices do less computation or communication, maybe people can think it is fair to just make them have worse accuracy. But again, I think it depends on on the goal of your particular system.
Okay.
Is there like a physical?
Ah, sorry. Yes, one more question, and you're here.
Thanks, interesting talk. So I want to understand, is the basic thing here that your evaluation set on what you're evaluating is very different from the production, deployment? So essentially you're saying that because your evaluation isn't the same, your performance will degrade, right? Because I couldn't think as the system as one confounder. There could be other confounders that if you don't have in your evaluation, you will have these kind of problems in production.
So sorry, can you repeat the question?
Yeah, what I'm trying to say is, so you're saying because of this system heterogeneity, your performance would degrade, right, in these lower systems. So let's say the system is one kind of confounder. You could have other such problems because of which your performance would degrade in a subset of recommendations. So what I'm saying is the essential problem that your evaluation is, where you're evaluating that population is distributed differently from your production population?
Sorry, I don't think I understand the question correctly.
I'll
Can
check
we
with you later.
take it offline?
Yeah, maybe that's a good idea to chat after the session on that.
Okay.
So thank you
Thank you.
again for your presentation. Our next speaker joined